Hi everyone. Today let's talk about section 4.4, optimization problems. So remember there are two types of application problems in Calculus 2. The first one is related rates. The second one is this optimization problems. So these two topics are the most challenging topics in Calculus 1. Okay, so please listen carefully, and I will also suggest you to compare this session with the session 3.10. Okay, then you can note the similarities and the difference, and then we can solve the confusion as well. Okay, big idea. Optimizing a quantity means finding the extrema of that quantity, which implies finding where the first derivative of the function describing the quantity is 0. Big skills. You should be able to write a function that describes a real-world situation, then find the extrema of that function, and make sure the extrema are within a reasonable range of physical values, i.e. no negative volumes, no negative time, no negative length, etc. Okay, so here are the steps for optimization problems. Step 1, identify what we are looking for. What is the unknown quantity to be optimized? So remember, we want to sketch the picture, okay, and we want to name the variables. Okay, for what is changing, give it x, y, a for area, v for volume. And what is constant? If it's constant, just give it the number. Okay, we don't need a variable for that. Okay, step 2. We already draw the picture in step 1, so okay. Oh, so actually we combine step 1 and step 2 together. Okay, and then, so step 2, we list the relations. We want to write the equation for the unknown quantity. Okay, and then step 4, we want to express the unknown quantity as a function of a single variable. So here we want to optimize what quantity we want to optimize. And then we learned in the previous sessions, how do we find extreme values? We take the derivative, we find the critical points, and then we use the first derivative test to find the local maximum or minimum. So among all the local maximum, the biggest values will be the global maximum, okay? And sometimes we might not have global maximum, so it really depends on the function. Okay, so our goal is to express the unknown quantity as a function of a single variable, because we are just learning single variable calculus. Okay, in calculus 3, we will talk about multivariable calculus. But right now, you should be able to express the unknown quantity as a function of a single variable. Okay, step 5. Differentiate the function. Test the critical points and endpoints in the domain of the function to find the global maximum or minimum. Okay, so those are the steps. So here are the table of the common figures and the formulas. Okay, so we have the 2-dimensional and the 3-dimensional. Okay, for 2-dimensional, we care about the area and the perimeter. Okay, so actually we went over this table in the session 3.10. Okay, so if you want to go into detail, like how we derive the formulas for each of the geometry figure, you can go to our videos in session 3.10. Okay. All right, so let's start the problem. Example 1, Suki wants to make an open top rectangular box with a bottom and 4 sides but no top out of a piece of paper that is 8 by 10 inches. Okay, so we have a piece of paper that is 8 by 10 inches. To do this, she cuts 4 equal size squares out of the corners and then bend the sides. So I bend the sides, then I form a box. Okay, so imagine it's like Halloween, but I don't have a bag. I use a paper to make a box, and I'm gonna fill the box with candies. What size of the square should I cut out to maximize the volume of the box? So I want to get more candy, so I want to maximize the volumes of the box. Okay, so we are looking for the size of the square, so let it be x. Then all the squares are of the same size. Okay, so we want, what is our goal? Our goal is to maximize the volume. Okay, let the volume be V. So now we have set the variables and we draw the pictures. So now let's go to step 2. We find the relations. Okay, so what is the relation between V and X? Okay, so let's look at our picture. So our picture, so this is X, this is X. Then what is this guy? This guy is actually 8 minus 2x, right? How about this guy? The total is 10, and this is x, this is x. So what is this guy? Okay. Oops. Okay. So this guy is 8. Oh, sorry, it's 10. 10 minus 2x. Okay, so in this new picture, the box picture, we have this guy is 8 minus 2x, and this guy is 10 minus 2x, and the height is actually x. Can you imagine? I strongly recommend you to get a piece of paper, cut the corner, and bend up the sides. Okay, then you can see it. Alright, so we get a rectangular box. What is the volume? Is the length times width times height. Okay, see, this is a function of one variable, x. So we're ready to differentiate and find the critical points and find the maximum or minimum. Okay, but in order to differentiate it, you can see this is a product of 3 terms. I don't like product rules, so what I'm going to do is to distribute everything. Okay, so 10 minus 2x times 8 minus 2x. So 10 times 8, right? So 10 times 8 is 80. 10 times minus 2x is minus 20x. Minus 2x times 8, minus 16x. Minus 2x times minus 2x plus 4x squared, right? Okay, I want to reorder it. So let me distribute the x and I reorder it. So this guy times this guy, I get 4x cubed. And then minus 2x minus 16x, we get negative 36x. Times x, we get negative 36x squared. And then plus 80x. Alright, everyone. Okay, and then, so we are ready to differentiate, right? So v prime is 3 times 4 is 12x squared. And then, 2 times 36 is 72x plus 80. So far, so good, everybody. Can you see a common factor here? Alright, I see 4 is a common factor. So what is left? We have 3x squared for so 1 and 18x, right? And this is 20. Alright, so we get a quadratic function. Okay, how do we solve this? So we want to set it equal to 0. By the way, if you try to factor it, you will see we're not able to factor it. So and that happens in many real life situations. We might not get a nice number, right? So it's okay. Quadratic. We have the quadratic formula. 2a, so we want to have this guy is 0. So a is 3. So 2 times 3 is 6. Minus b. B is negative 18. So we have negative 18 is positive 18. And then we have b squared minus 4ac. Right? All right. So what is that? Let me plug this in my calculator. So if you have a calculator, I strongly recommend you to try to plug this number in your calculator, because knowing how to use your calculator is also very important. Okay, so the numerator, I have 18 plus square root of 18 squared minus 4 times 3 times 20, and then don't forget to put another parentheses and then divide it by 6. Okay, so the answer is I get 4.5275. Okay, so that is the plus. And when I plug in the minus, so you don't need to type the entire thing again. You just go up to that formula and change the plus to minus. I get 1.47247. So that's like 247. So it's like 25. All right. So we have two answers. Which one shall we take? Okay. Let's figure out the domain. Okay. So what is the domain of x? Okay, so the domain of x, think about what's the smallest x can it be? Well, it can be 0, right? 0, it means you cut nothing. You didn't cut anything, right? How big can it be? Well, we have a paper that's 8 by 10. Well, the biggest is, well, the biggest is like you cut all these pieces. So this is 8. So this is 4. This is 4. So if you cut out when x is 4, what you left is actually you just get a strip of paper that is 8 by 2. Yes? Okay. So that is our domain. All right. So next, remember draw the diagram. So we have 0 and 4. That is our domain. And which critical point lies in this range? Yeah, 1.4725 lies in here. Okay, and then we do v prime and v. At the critical point, v prime is 0. This is how we get this critical point, right? We set the derivative equal to 0. Okay, and then on this piece, let me use a different color. Okay, so here we want to talk about plus or minus, right? Here we want to talk about increasing and decreasing. Okay, so what do we put here? Well, do we have a point in this range? Yes, 0. So when we plug in 0 into the v prime, what do we get? We plug in here. So when we plug in 0, we have 4 times 20. So 4 times 20 is positive. So we have positive here. How about next? So we plug in 4. 4 squared 16. 16 times 3 is 48. 48 plus 20, 68. And then 4 times 18 is 72. So we get negative here, okay? So that's why my v, if my v prime is positive, my v is increasing. If my v prime is negative, my v is decreasing. So if you have increase and decrease, what do you call this guy? Yes, local max. And actually, you can see here, because it's on a closed interval. So this is not only local max, it's actually global max. Can you see? This is actually global max. And the global mean is one of these points. Okay? Alright, so that's why we can answer a problem like we get maximum volume when my x is 1.4725 inch. Okay, so that answered the problem. What size of the square should I cut out to maximize the volume of the box? All right. Okay, how about you pause here and try to work on example 2? Are you done? Let's continue. Okay, check our work. A manufacturer needs to make a cylindrical can that will hold 1.5 liters of liquid. Determine the dimension of the can that will minimize the amount of materials used in its constructions. Okay, we want to make a cylindrical can, so that's a cylindrical can. All right, sorry, I didn't draw a beautiful can here. Okay, so a can, cylindrical can, what do we need? We need radius and height, right? Okay, we know that our goal is to hold 1.5 liter of liquid. Well, what is liter? So actually, 1 liter equals 1,000 centimeter cube. Okay, so 1.5 liter. So volume is 1.5 liter, but I don't want liter. I want centimeter cube. Okay, then so that will give us 1500 centimeter cube. Okay, because we want to talk about the dimension. The dimension is like length, and here the length should be centimeters. Okay, so this is the volume. We have the volume that is fixed. Okay, and so we want to determine the dimension of the can that will minimize. So our goal is to minimize the amount of material used in its constructions. So that is actually surface area. So let's call it A. Okay, so this is the first step. We draw the picture, name the variables, and figure out what we want to maximize or minimize. The second step, we want to write down the relations. Okay, so volume is involved. Volume for cylindrical can cylinders is pi r squared times h. Okay, and we know what is V. V is 1500 cubic centimeters. And then surface area, this is what we're looking for. Okay, so remember cylinders, we have top circle, bottom circle. So 2 copy of area circle is pi r squared. And when we cut it and open it, the sides, we actually get a rectangle with the length is the circumference of a circle, 2 pi r, and the width is the height h. So that's why this rectangle is length times width, 2 pi r h. Well, here we have, this is A is a function of 2 variables. So we need to eliminate one of the variables so that we have a function of 1 variable. But how do we do it? Well, we can use this formula, right? Questions. Do you want to express h in terms of r, or you want to express r in terms of h? Which one is easier? Yes, we express h in terms of r. This is easier because if you express r in terms of h, you need to take square roots. So we don't want to work with square roots. So let's express h in terms of r. So now we can plug in. Okay. So h is 1500 over pi r squared. Now let's see, pi cancel, r cancel 1 copy. So we have 2 pi r squared plus 2 times 1500 is 3000 over r. So far so good, everybody? All right. Next, we're ready because this is a function of one variable. Let's go ahead and differentiate it. So different derivative of 2 pi r squared is 2 pi times 2, so 4 pi r. Okay, this guy is like 300 times r to the negative 1. Derivative of that is negative 3000 r to the negative 2. When you see the negative exponent, don't forget, it means that guy is actually lives in the denominator, right? And then we want to take the common denominator. This guy would become 4 pi r cubed. Okay, so this is our derivative. Okay, so this is our derivative. What do we want to do? We want to find critical points, but because this is a quotient, so we need to let the numerator equal to 0, and we also need to let the denominator equal to 0. Okay. So numerator equals 0, we solve for that. 4 pi r cubed is 3000. So then r cubed is 3000 over 4 pi. Can we simplify 3004? Yes, that is 750 over pi. And then so r is, you take the cube root of 750 and pi. And then this guy, we just got r is 0. Okay? Next, let's figure out our domain. So we have r. How small can r be? Well, 0. It cannot be negative, but it cannot be 0 because if it's 0, your volume is not gonna be, your volume will be 0, so it's not gonna be 1.5. Okay, how big can r be? Well, as big as you want, but your h is just gonna be very, very small. Okay, so that is our domain from 0 to infinity. And then this guy is not in our domain, so that's not the critical point. So we only look at 750 over pi and then take cube roots. And then we want to put a prime and a here. Okay, so a prime, we know this is a critical point, and how do we get this number? So we actually get this number by letting the numerator is 0. So the numerator 0 means the derivative is 0. Okay, how about this guy? So we think about it, I know this is a number, but we don't know what is that. But you can imagine what happens if your number is close to 0. If your number is close to 0 and you plug in, let me use a different color. You plug in it here. Okay, so a number very close to 0. So this guy is like almost like 0. So that's why we get negative 3000. So it's negative, but the denominator is always positive. So the answer is negative. Okay, here we can think about a big number, okay, maybe 1000. Then you see this guy, the numerator is going to be positive and the denominator is also positive. Okay, so that's why my a is going to be decreasing, increasing. So if you have decreasing, increasing, what do you call this guy? Local mean. And in fact, here is global mean as well, because this goes up and then this is the only this is the global mean as well. Okay, so that's why we say get minimize area, surface area, when my r is 750 over pi to the 1/3. Because it's asking dimension, you also need to find the h. H is here, so h is 1500 over pi. R is this guy, 750 pi to the 1/3, but r squared become 2/3. Okay, so you just leave your answer like that, or you can put this in your calculator. Okay? All right, that is example 2. Okay, the good thing about the video is if you get tired, you can pause it and have a break. Maybe have some juice, chips, and listen to some music. Okay, all right, let's continue with example 3. Yeah, I know this session is quite, this is one of the challenging session, okay? Some problems can be very complicated, especially so I give you extra exercise from your textbook. So if you go to our course website, you can see more exercise in session 3.10 and 4.4. So I also give you solution. Some of the solutions you can see I wrote hard problems. So you don't need to solve it by yourself, but I hope you can understand the solution, okay?